Welcome. Today we're going to look at derivatives of exponential and logarithmic functions. Let's take a peek. Main objectives here are finding the derivative of an exponential, then a logarithmic function, and then we're going to use a technique called logarithmic differentiation, which is a fancy way of using implicit differentiation. So derivatives of logs and exponents, we're going to start with the exponential function. So if we consider the function f of x equals e to the x, the power rule doesn't apply here because the power rule only applies if the base is variable and the power is fixed. And here I have the reverse of that. So that means we have to resort to the limit definition. So define the derivative. I need to take the limit as h goes to 0 of e to the x plus h minus e to the x all over h. And then just using a little bit of algebra on this, we can rewrite the first term as e to the x times e to the h. And then we can factor that e to the x out of the numerator. And since it doesn't have an h in it, we can pull it all the way out of the limit. So we get e to the x times the limit as h goes to 0 of the stuff with h in it, which is e to the h minus 1 over h. So then the big question is, well, what is this right here? And we actually explored this limit back in chapter 2. So let's take a look at it now in Desmos. So we have a fraction, and we're going to use the variable x instead of h here. So we have e to the x minus 1 over x. So we get that right there. And we played around with numbers before and zooming in. Now it's undefined at 0, but you can see a little to the left, it's a little above 1, or a little to the right, it's a little above 1, a little to the left, it's a little below 1. And our exploration led us to that this limit seems to be 1. So based on that numerical work, we're just going to claim that it's true, so that this limit is actually just e to the x, which is kind of nice. So we have a function whose derivative is itself. And you may ask yourself, well, what other functions is that true for? So you think about that and get back to me if you figure it out. Dealing with other bases, we can apply a little trick. So we know that if f of x is e to the x, then f inverse of x would be natural log of x. And these two functions, again, are inverses so that when we compose them, they cancel each other out. So for example, the natural log of e to the x is equal to x. Okay. So what I'm going to do is look at a new function now, and I'm going to look at y equals 2 to the x. So if we apply the limit definition, we'll get a similar thing. We'll get a slightly different limit here. We'll have a 2 here instead of an e. But I'm going to do a little algebra with this right here. And so my claim here is I can rewrite this sucker as e to the power natural log of 2 to the x. And that comes from the other version of composing a function in its inverse. So natural log of e to the x, or I can compose as e to the power natural log of x, and that's going to equal x. But the bottom line is whatever I take the natural log of here is going to end up over there. So here I'm just throwing a 2 to the x in there, right? So this is just definition of inverse functions for logs and exponentials. Cool thing about this, however, is there's also a property of logs that you can take the power of its argument out. So I can rewrite this again as e to the power x times the natural log of 2. Natural log of 2 is just some number. So now I can take the derivative of this for 2 reasons. One, I know the derivative of e to the x, and I know the chain rule. And so the chain rule is going to apply because I have something other than x as the power here. So for dy dx in this case, I'm going to get the derivative of e to the something is something, e to the something. Oops, wrong thing there. 2. And then the chain rule says you got to multiply by the derivative of this power here. And so the derivative of the power is just natural log of 2. Now, cleaning this up a little bit more, e to the power x natural log of 2, well, that's just a fancy way of writing 2 to the x. So the derivative appears to be 2 to the x times the natural log of 2, which we usually write in the other order. So I'm going to say the derivative is natural log of 2 times 2 to the x. And there's nothing special about 2 as the base, so we can kind of generalize this. So a couple of formulas that are going to be good to know. The derivative with respect to x of something like e to the u, where u is a function of x, would be e to the u times u prime. Another important formula would be the derivative with respect to x of some other base to the power, let's call it u again. We're going to get a natural log of the base, according to our previous example. And then we're going to get a b to the u, and then the chain rule says multiply by u prime. So exponential functions, e is the most common one, but sometimes we have other bases, and so that's how we deal with other bases there. All right, next problem. Let's let g of x equal the natural log of x. So g of x is an inverse function. So if I say that f of x is equal to e to the x, then that means the natural log must be f prime. So I could use our inverse function theorem to do that. I could also use implicit differentiation. So for example, if I rewrite my natural log as y equals the natural log of x, I can rewrite this in terms of an exponential equation. And that would be e to the power y is equal to x. And so now I'm just going to differentiate this implicitly. So if I take the derivative on each side, e to the y, derivative with respect to x of x. On this side here, again, I'm assuming y is a function of x, so the chain rule is going to apply on the left. So the derivative of e to the something is e to the something times the derivative of the exponent, which I'm just going to call y prime. On the other side, the derivative with respect to x of x is just 1. So then I get y prime is equal to 1 over e to the y when I solve. But I know y is equal to the natural log of x. So rewriting this again, I get 1 over e to the natural log of x. And I also know that log base e and e to the power cancel each other out, so the answer must be 1 over x. So what we've just discovered here is that the derivative with respect to x of the natural log of x is equal to 1 over x. What if it's not natural log? What if it's some other base? Glad you asked. So let's give another example. Let's look at log base 2. So if I take, I want to take the derivative with respect to x of log base 2 of x. So what I'm going to do with this, I'm going to apply the change of base formula for logarithms. You may remember that from way back in your algebra career, last year, hopefully. To change bases, you pick a new base, like natural log, and then to adjust, you divide by the natural log of the old base, in this case, 2. Now, natural log of 2 is just a constant, so I can pull that constant out of the derivative. So I'm going to have a 1 over the natural log of 2 on the outside, and then I just have to take the derivative of the natural log of x, which we know is 1 over x. So I get, for a derivative here, 1 over natural log of 2 times 1 over x. And so this is going to work for any base. So we can generalize and say if we take the derivative with respect to x of any old logarithmic base, let's call it base b, and let's throw a u in there and use the chain rule too, then we're going to get a u prime from the chain rule over the natural log of the old base times x, or sorry, u. All right, so we have derivatives of logarithms, we have derivatives of exponentials. Next, we're going to deal with another strange case, and we're going to whip out an idea called logarithmic differentiation. So logarithmic differentiation is a technique we're going to apply when we have something odd. You can also apply it to even cases. Sorry, bad joke. Consider the function x to the x. So the power rule doesn't apply here because the base is variable. And the e, or base, the exponential rule doesn't apply because the base is variable. So that's a problem. So what I can do with this is take the natural log of each side. And so that's going to give me the natural log of y equals the natural log of x to the x. In this case, it's only going to apply when this is positive here. And this function gets pretty sketchy when it's negative. So if we look at that in Desmos quick, clear that sucker out, and look at y equals x raised to the x, to the x to the x. Some weird stuff is happening on this side that's kind of hard to see. Desmos can't even really handle it. On the left, there's a scattering of points, and on the right side, we have this interesting curve that looks like a parabola, but it's not. A cross between a parabola and exponential, you could say. Anyway, it's its own thing. And then here, I can just proceed by using implicit differentiation. But before that, I'm just going to note that the logarithm has the property where powers pop up. So the right side is going to become x times the natural log of x. Other side, I have natural log of y. And then we just implicitly differentiate here. So we're going to take the derivative with respect to x of the natural log of y. And same thing on the other side, derivative with respect to x of x times the natural log of x. So we have the product rule going on the right side. We're going to have the chain rule going on the left side. So the derivative of the natural log of something is 1 over that thing times the derivative of the inside. Other side, I'm going to have to apply the product rule. So the derivative of x is 1 times the natural log of x. Then we add on, leave the x alone, and take the derivative of the natural log of x, which is 1 over x. Cleaning that up, I get, on the right, the natural log of x plus 1, as long as x isn't 0. And then solving for y prime, I can just multiply y to the other side. So y prime is equal to y times the natural log of x plus 1. And y is really x to the x. So then I get this interesting multiple, x to the x times the natural log of x, which, if you think about it, is related to the exponential rule, which says the derivative of some base to a power is itself. So there's the 1 times. But the base is different, so I have to adjust by multiplying by the natural log of the base. So there's kind of 2 things going on at once with this thing. So it is similar to the exponential rule, but different. So again, that's logarithmic differentiation. And there's many applications for it. You're going to get to play with that in your homework, but that was just one basic example. So do good math, have fun, see you in the future.